Okay, today we're going to continue with voltage and look at a new formula and do some questions on how we can put these formulas together to solve a bunch of different types of questions. So first off, remember from yesterday we were talking about if we have a charged plate, we have one that's positive, one that's negative, we're going to get charges move through that in a uniform electric field. So the idea then is to remember, the key thing is to remember that whatever the charge is, so if we had a positive charge inside that, right now it has high potential energy because it's going to be repelled from the positive, attracted to the negative, so it's going to move through those gaps from high potential down to low potential. And remember, the electric potential difference between those plates is what we call voltage. And remember, our voltage then was how much energy per coulomb of charge is gained, whether it's kinetic, so in this case the proton or positive charge will move downwards, so it's going to be gaining kinetic energy as it goes. Or we could do the reverse and push that positive against the electric field, and that would be how much potential energy we're going to gain as we go the opposite direction. And the same thing would happen with a negative. If we put a negatively charged object in there, right, the negative is naturally going to go upwards, so that would be gaining voltage or gaining potential energy, or kinetic energy, sorry. And if we had it the other way around, we push it against the electric field, we'd be gaining potential. So it doesn't really matter which type of energy we're talking about, the voltage tells you the same amount. It's going to be how much energy per coulomb, just depending on which direction you're going and whether it's positive, negative, and so on. So what we're going to look at today is how can we get a new formula. So because we're going to be gaining energy, remember work is force times distance, but we also know that work is change of energy. And if we're going, let's stick with potential, so if we're pushing this charge against the electric field, that change in energy then would be equal to the potential energy it gains time, which was equal to force times distance. So I'm going to just add the change in energy on here. So our change of energy will be EP equals force times distance. And it doesn't matter whether we use potential or kinetic, it's the same answer anyway. Okay, but we also know that from before, we know that voltage equals change in energy over Q. So if we combine these two formulas, we can actually substitute the force times distance in for Q, or for energy. So voltage equals force times distance over Q. But we also know that electric field equals force over Q as well. So you can see that within this new voltage formula, we have force over Q. We're dealing with electric force in this case, so they're the two of the same things. So if we combine those two together, we actually get a new formula that is voltage equals electric field times distance. And your formula sheet changes it around a little bit. They write it as electric field as absolute values because we don't care about positive, negative direction. We just worry about the charges. And we write it as change in voltage over change in distance. So our voltage, remember, is the joules per coulomb, or whatever we want to call it, but let's leave it in volts. And our distance would be the distance between the plates, between the locations that the charge is moving. So that'll be in meters. So you can see that we actually get our electric field can be in volts per meter, or what we had before with this first formula, we had newtons per coulomb. Okay, so that's the key thing to sort of remember, is we got two different formulas now for electric field. We can use force over charge, which will give us newtons per coulomb, or now we can use voltage over distance, which gives us volts per meter. Okay, so let's do a couple examples. So the first one is we got parallel plates 16 millimeters apart, and we want to get an 800 newtons per coulomb electric field. So the question's asking, what is our voltage? So if we just take this new formula, we'll go electric field times distance, and plug it in. So we'd have 800 times 16 millimeters, so 16 to the negative 3, and that'll give us a voltage of 12.8. Okay, so it's pretty easy formula to work with. The next part of the question now is how much work is done if we move an alpha particle from the positive plate to the negative plate. Okay, so we want to calculate the work or the energy, so we're looking for change in energy. We know our voltage and we know how much charge an alpha particle is, so we want to basically use the old formula now. So we know that voltage equals energy over charge, so we can solve it for energy by going voltage times charge. So we have 12.8, and a alpha particle, remember, is 2 times our base charge, so 3.2 to the negative 19. Multiply those out, we would get 4.10 times 10 to the negative 18 joules. Okay, or if we wanted to leave it in electron volts, remember, we would just go 12.8 times 2, right? 2, the value of 2 electrons, or 2 base units. So 12.8 times 2 would give us 25.6 electron volts. So those two answers are the same, just depending on which unit we want to use. Okay, and the last part of this question is that energy gained, is that 4.1 to the negative 18, is that in kinetic or potential energy? So we just got to kind of think about it. If we have an alpha particle, and it says it's moving from the positive plate to the negative plate, the alpha particle is positively charged, so that's going to be the natural movement, so it should be kinetic, right? We're decreasing potential, increasing in kinetic, so it would be kinetic energy that's getting gained. One more example. So this one, it says we have an alpha particle moving between two parallel plates, and they give you the potential difference. They give us our voltage. The question is, what is our force? So same type of thing. We're going to use our two formulas again. So we're going to use our electric field is voltage over distance first. So you'd have 130 volts over 2.7 to the negative 2. And that gives us an electric field of 4815 volts per meter, or newtons per coulomb, however we want to rate it. And now the second part of the question is, what's our force? So we'd use our old formula, electric field equals force over Q, and that's electric force, obviously. So we would have electric field times Q. So just take our answer we just figured out, 4815, and times it by the charge of a alpha particle, and that'll give us a force of 1.5 to the negative 15. Okay, so pretty basic questions. We're just using the two formulas, our voltage one that we did yesterday, the new voltage one, and then I'll see our electric fields from before. So we can do lots of questions with these formulas, but remember, with these new formulas, we can also pull back old stuff that we learned in Physics 20, and we can do a variety of different types of questions. And that's really the only challenge to this stuff, is sort of figuring out which way you're going to go, which formulas you're going to use, and so on. So with the new stuff, we can still use force equals mass times acceleration, but in this case our force is dealing with electric force. Because we have acceleration, we can still use any of our old acceleration formulas. We can use conservation of energy stuff that we did in Physics 20, all kinds of choices. Okay, so all we have to basically do is think of this as terms of an object moving, or something that has kinetic energy, potential energy, acceleration, velocities, all those kind of things. Okay, so keep in mind that most of these questions are going to be involving electrons, protons, alpha particles, so our charges are going to be pretty small, 1.6 to the negative 19, or 3.2 if it's an alpha particle, and our mass of electron is pretty small too. All of that data is on your formula sheet, so you don't need to memorize it, but as you use it over and over again, you're going to easily remember these numbers anyway. Okay, so we're going to do another example, and this time I'm going to show you sort of two different ways or two different approaches you could solve it. So the question is, we have an electron moving between parallel plates. So in this case, if we have an electron that's inside the parallel plates, and the way I drew it, obviously it's going to move upwards towards the positive plate. So we have our distance, 4 centimeters, and we know the voltage is 20 volts. We got everything that we need. So the question's asking, what is its velocity when it hits the other side of the plate. So it's starting from rest, it's looking for basically final velocity. So first thing I kind of jotted down here, sort of the way you could solve this one, is first find the electric field. So we'd have electric field is voltage over distance. So that gives us 20 volts over 4 centimeters. So that gives us an electric field of 500. Okay, so we've got our fields. So now the next thing we could do is use our electric field formula to find force. So electric field is force over Q. So our force then would be our electric field times our charge of an electron. And that gives us an answer of 8 times 10 to the negative 17 newtons. Okay, so now we got our force. So now the next question is, if we have force, we must have acceleration. I'll just keep writing it here, but we could use force equals mass times acceleration. So our acceleration would be our force answer that we just calculated, divided by the mass of an electron. And that gives us a fairly large acceleration, 8.78 times 10 to the 13. And that'd be in meters per second squared. So pretty fast acceleration, but because it's a particle or an electron moving over a relatively short distance, it should technically have a pretty good acceleration. Now the last step is, now that we know acceleration, we could be looking for our final velocity. So just like we would do in Physics 20, we'd have our final velocity is what we're looking for. In this case, we know our initial was 0. We just calculated our acceleration. And we also know our distance of the plates was 4 centimeters. So now we can just basically pick one of our old acceleration formulas and solve it that way if we want. So the one I'm going to use is Vf squared equals Vi squared plus 2AD. Plug all the numbers in. I won't bother plugging it in, but we should get a Vf of 2.7 times 10 to the 6. Okay, so you can see 4 different formulas. We're combining electric formulas with our old acceleration and velocity stuff, and we do get a final velocity. Main difference between what we did in Physics 20 to now, you can see the numbers are huge. Like we're talking, billions of meters per second as that electron shoots across the gap, which is always going to happen, right? In terms of electricity, the forces are stronger. That means our speeds are going to be a lot stronger as well. Method 2, I just want to show you on here, maybe a quicker or easier way for you to understand this, and I want to just show you that we do get the exact same thing. So for method 2, I'll do it over on the side here. The first thing we want to do is calculate our voltage, which we can do, right? We know our we want to use the voltage to calculate energy. So we're going to use our voltage formula, which was energy over Q. So that means our energy would be voltage times Q. So our voltage was 20, charge of electron 1.6 to the negative 19, and therefore we get an energy of 3.2 to the negative 18 joules. Okay, and now that we know, if we know the energy, we know that that's going to be speeding up, so that energy is going to go from potential, that's our total potential, it's going to get converted to kinetic, so we can just simply use our energy formula from Physics 20 for kinetic energy, and we can just use energy equals 1/2 mv squared. So we can plug in our 3.2 to the negative 18 equals 1/2 times mass of an electron times v squared, and then solve it, rearrange it and solve it for v, and you'll see you get exactly the same answer. Okay, so either method, totally fine. The idea then is just which one do you prefer, which one do you think makes more sense to you, and it's just going to depend on your preference. So just like in Physics 20, remember we could always use the old acceleration formulas, but once we use conservation of energy, that worked as well. So the same sort of application still happens here. So part B to the question now is, we just calculated the maximum velocity. So now the question is, what would happen if we only move it 1 centimeter? So instead of going across the whole 4 centimeter plate, what happens if it's only going to go 1 centimeter? So the only thing we could do differently is, if we're going to use method 1, remember we used our Vf squared formula So the only thing that we do differently is we plug in a distance of 1 centimeter instead of 4 centimeters. So our VI was 0. Our acceleration we calculated was 8.78. And our distance we put in as 1 centimeter instead of 4 centimeters. So we get a final velocity once you plug all that in and square root it. We get 1.3 times 10 to the 6. Okay? Or we can kind of go back to what we did with the electric field stuff. So in this case, we'd have electric field. So we want to find electric field, which is voltage over distance. So if we solve it for voltage, we would get 500 times only 1 centimeter now. So that gives us 5 volts. So remember in our formula, this is change in voltage and change in distance. So what that means is to go only 1 centimeter, we've gone 5 volts out of the 20, which makes sense. 1 centimeter out of 4 is a quarter, so our voltage should be a quarter as well. So now that we got our volts, we can figure out what the energy is by using energy over Q. So our energy would be voltage times Q, so 5 times our charge of electron, we get 8 times 10 to the negative 19 joules. And then the last step is take that energy and solve it for velocity. So that energy will be kinetic energy. Solve it for V. I won't bother plugging it all in, but we do that, we'll get 1.3 times 10 to the 6 as well. So you can see it sort of just depends. The first one I think is a lot easier. Once we used acceleration formulas, this is one step. This one we need about 3 formulas to get, but we do get the exact same answer either way. And I also added a method 3 on here, which I just called it ratio. And the idea is just keep in mind that if our original voltage was 20 volts and our original distance was 4 centimeters, so if our particle went halfway, then it had a change in voltage of 10 volts. If it went only 1 centimeter, like we just did, and it doesn't matter where it is, it can be at the start, it could be at the end, so in this case our change in voltage would be 5 volts. And then the final centimeter would also be 5 volts, and so on. So you can always use ratios to help you sort of figure out how much voltage it's going to go through. So if our total was 100 volts and we had 5 centimeters, then it'd be 20 volts per centimeter or however. You just basically break it up into proportions, and you can always do your voltage like that. You can't do the velocity that way, though, because it's accelerating, so it's not going to be equally proportioned. The energy would be, right? Halfway the energy would be at half, and so on. So you could actually maybe do this part B question a little bit easier. If we went back to part A and figured out what our energy was, so we had over here, we had an energy of 3.2 to the negative 18, so that was for the full distance. So we could just take our energy of 3.2 to the negative 18, and we know we're only going a quarter of the way, so we could divide it by 4. So that should give us our same answer that we had. Okay, so you could proportion the energy, so we get the same answer, and then once you have that, you still have to do 1/2 mv squared to get velocity. So we're going to do lots of practice questions in a booklet, so we'll spend a day or so working on these types of questions, and you'll get the hang of when to use which formula and what are all your different options. And that's all.